Okay.
Hi, this is Gene Fry. I received my PhD from Cornell in 1989. I've been studying climate change for 30 years now. I worked for the Massachusetts Utility Commission for 13 years and shorter stints at Northeast Utilities, mostly energy efficiency, the energy office in Maine, and writing for various environmental newsletters. I've spoken to some 60 audiences on 3 continents, been keynote speaker on 3 continents, and I've come to talk to you today about climate change and especially about feedbacks that will drive future warming. So I'd like to share my screen with you now. And here goes. Let me put my picture down here and start up my slideshow. Okay. Why carbon neutral is way not good enough. So we're going to cover introduction, climate history, and we'll pause, and then climate change drivers, another pause, putting those feedbacks together and looking at climate futures, another pause, and then looking at what we need to do, and then another pause. There are additional slides which I will not be showing, but it would be available on the website. So I think I'd better minimize this. Whoops. So the key misconception is when we stop putting carbon in the air, Earth's temperature stops rising. That's not true. It's only when the feedbacks have all played out that the temperature stops rising. Earth has had this much CO2 in the air before, millions of years ago. It's much hotter then. This study examines the factors that will make it that hot again. Where I started, the map's on the next slide in 1989. Another part of that study found that US food production would fall 30 to 50% by 2050. That got my attention and has held it ever since. So here's what I saw. This is looking at drought, supply-demand drought index. This was at a conference in Raleigh, North Carolina, presentation by David Rind, whose boss is Jim Hansen. Looking back in 1969, we see a world where the greens are about the same as the oranges, so it's normal. Looking in their future to 1999, our past, you see that once a decade drought in orange is covering a wide band. It's still dry in Antarctica, drier than now. Looking 30 years farther in their future, which is also now in our future, a lot of wet along the Arctic, but a much bigger and broader band of once a decade drought, and you see bigger patches of once a century drought in dark brown there. Fast forward 30 years, you've got doubled CO2. More important, you've got plus 4 degrees Celsius. We're currently about 1.1. You see once a century drought covering about half of Earth's land mass. A lot of rain in the Arctic, and you're starting to see a lot in the Antarctic. So this is using climate model developed by NASA out of Jim Hansen's group. And there's the journal citation. So here, this describes where we are. We've run off the cliff and we're surprised, but we don't know that ran off the cliff very well. We've got our suspicions. There are going to be lag effects. So feedbacks, mostly albedo, that means reflection, means it's going to get much hotter. So I'm sure all of you are aware of the greenhouse effect. This is one diagram, incoming radiation, short waves, Earth heats up, gives off long wave radiation, infrared, and some of that's intercepted by greenhouse gases. The more greenhouse gases you get, the more is intercepted and radiated down, and the surface warms up. The other thing is the albedo effect, and that's what's often neglected. So here's an example involving snow, ice, and water. When most of the energy is reflected, Earth does not warm up as much. When most of it is absorbed on the right, Earth warms up a lot more. If you change a dark surface, to a lighter one, on the other hand, that cools Earth. But this diagram is changing a light surface to a dark one. So the albedo effects come from changes, area, density, and color in clouds, sulfate haze, sea ice, snow ice, and land ice. Those are the major players. Not covered in the study are soot from fires, forest and peat, and incomplete combustion, nor is vegetation covered. It's not clear if those are warming or cooling on balance. That's why I did not include them, at least in part. So you know about the greenhouse gases. The greenhouse effect on Earth's surface is about 33 degrees Celsius. Water vapor is the #1 greenhouse gas. As Earth warms up, evaporation increases water vapor in air. This amplifies warming from other greenhouse gases and from albedo changes. Carbon dioxide is the most important greenhouse gas that we have choice about. The next most important one is methane, CH4, basically natural gas. Those are the major sources, somewhat in order of prominence, although they're all fairly close. There are other greenhouse gases. And this is a diagram of greenhouse gases by wavelength. You see a big CO2 over on the left. H2O is on the far right and on the far left. Methane is over toward the right, and there's also one for ozone. So this is where the outgoing infrared gets absorbed. The visible light is well off to the right. So about global climate models. Earlier ones often omitted large-scale changes in permafrost, sulfates, and clouds because they did not understand them well enough. They often also underestimated how fast the Arctic sea ice would melt and climate sensitivity. They also stopped in 2100. As things that were left out got put in, scientists said, it's worse than we thought. We've heard that repeatedly. So the next section is to look at climate history and a little bit of analysis. We can learn lessons from the distant past. Notice the red area where it's much warmer than now. Once it got cool enough, you started to get Antarctic ice sheets about 34 million years ago. So it can get a lot warmer than now. Temperatures can rise suddenly. That's what they're doing right now. And the temperature swings get wider when we have a lot of ice to melt. And we go between a high ice state and a medium ice state. Looking now at the instrumental thermometer record, this is NASA's record going back to 1880. You notice that land is warming faster than the sea surface. We've had 1¼ degrees Celsius warming when you average both of them over the last century. It's going up twice as fast over the last 20 years. At that rate, we'll exceed 2 degrees before 2060, and the land surface will exceed that in about 15 years. That's assuming current rates. You've seen the Keeling curve before about CO2 levels in Earth's atmosphere. This is not the sawtooth version because I'm using annual averages. It's up 47% since 1750, 40 of that since 1880. Methane is up a good bit more steeply. That's the maximum between the ice ages. We're ahead of that. Has consequences. Earth's 100-year surface warming rate is far greater than the previous record that I can find anywhere in the geological record. The last time CO2 hit this much, millions of years ago, Earth was much warmer, and seas were a good bit higher. Kansas was hot as Las Vegas now, and Florida was mostly underwater. This past is our guide to our future unless we change our CO2 concentrations. A little more detail, 14 million years ago, 430 to 465 parts per million, 10 degrees Fahrenheit warmer in the deep ocean. Seas were a bit higher, quite a bit higher. I mean, most of New York City was underwater, not all of it. Almost as high 4 million years ago. Sea surface was a good bit warmer, but not as much as when there was even more CO2. This means ice then was gone from almost all of Greenland, most of West Antarctica, some in the east. A lot of ice in the west is grounded below sea level. That's not counting the ice shelves. But so is 39% in the east, and there's a lot more east. East Antarctic ice then retreated far inland. That happened before. It's going to happen again. We face big lag effects. So we're looking now at ice core data from Vostok, about 900 miles from the South Pole, the coldest place on Earth, Russian station. Temperature, methane, and CO2, carbon dioxide at the top. So the temperature is still in the range there, but the CO2 level, and especially the methane levels, are way out of range from that period of time. So on to the next two slides. The next one, we're going to get rid of the time axis, plot temperature versus CO2 as blue dots. And the slide after that, we'll add in information from 4 million years ago, there are your sources, and 14 million years ago. So let's go on first to just looking at the ice ages and the trend lines that are the best fit to the data. So there we go. And you've got a temperature that covers 420 million years, and temperature at Vostok over on the left. And this is translated to an estimated temperature globally on the right using work by Snyder, Carolyn Snyder from 2016. Now we're going to put that together. And the green line, by the way, is using methane and CO2. The purple one is just CO2, which is what this graph says. So continuing, we've got two equations. The purple line's equation is as you see it there. And my analysis goes back a few years. And it's a reasonably good fit, but far from perfect. You can see the scatter there. It's a better fit if you also take into account methane. Now we're looking 4 million years ago and 14 million years ago, and you have both CO2 and temperature ranges there. I mean, these are 200,000 years, 400,000 years, so there's a lot of time for these things to vary. Today's methane level. So this allows us to estimate climate sensitivity, the increase in global surface temperature for doubled CO2. These are long-run equilibrium. The purple line, we plug in doubled as much, logarithm of 2, and you get 13. The long-run global sensitivity, you multiply by 0.6, and you get 8 degrees Celsius for doubled CO2. That's a lot more than the standard short one that's 3 degrees used by most climate scientists. So what does that translate to in terms of temperatures? With today's greenhouse gas levels, CO2 only, there's your equation using 412 parts per million today, 4.8 degrees Celsius above 1880, we're at 1.1 now. Add methane, there's the equation, 1860 parts per million of methane. That's 8 degrees Celsius. That's far warmer than now. And I think you'd call that a hothouse. And that's just from today's methane and CO2 levels. Now, how do we get to 2 degrees? There's our basic equation for our two principal greenhouse gases that we emit. So it depends on the one, it's kind of like A for CO2 and B for CH4. And you can vary those two and still get 2. One goes up, the other goes down. What we need to do is remove 3/4 of CO2 we've already emitted, any future emissions, and all our methane, past and future. Carbon budget is a rather pernicious idea, but we have less than 0 carbon budget, whereas many scientists relying on a bad model have said we have a lot left to burn and still hit CO2. Still hit 2 degrees. So perspective. We're concerned about the temperature of the air. That's that tiny little purple stuff almost on the 0 axis. It's 93% of the heat goes into the ocean, about 3% into melting ice, about 3%, 2% into warming up the land, and less than 1% really warming up the air. So we're going to look at where most of the heat goes, 93%, and the census scale. One of those tick marks is 100 years of US energy use. 3 of those tick marks is all the energy humans have ever used. So what we're seeing is gradually the slope is increasing. That means we're seeing acceleration in the amount of energy that Earth is absorbing. This is as a result of the enhanced greenhouse effect from our emissions, amplified by feedbacks. The oceans gain about as much heat every 3 years as all the energy humans have cumulatively ever used. We're going to pause here and take some questions. Hello again, this is Gene Fry, and I'm going to talk about climate change drivers, in particular feedbacks. Emphasis on albedo feedbacks, but there are others. So look first at tipping points. These involve feedbacks. This was a report in January 2006. What would make climate change accelerate so natural forces defeat our efforts to slow it? Disappearance of sea ice, carbon sinks fade in oceans and forests, methane released from permafrost. Those are the most important tipping points. Various people have pointed out various other ones, but let's just focus on those. Water vapor is the most important greenhouse gas. Some of these numbers have wide error bounds, but this is known rather quite precisely. 1.5 watts per square meter, 7% more water vapor corresponding to 1 degree Celsius warmer air. Now we're going to look at the primary albedo effects: clouds, sulfates, sea ice, snow, and land ice. Same ones I mentioned before. Half the sunlight reaching our atmosphere makes it to the surface. Barriers include clouds, sulfates, blue sky, and the ozone layer. So we'll consider each of those in turn, starting with clouds. Clouds reflect some sunlight away, cooling Earth. They also keep outbound heat in, warming Earth. Many factors affect them. At night and going up over mountains, air cools. Cool air holds less water, so it often cloud up in rain or snow. Clouds cover a little more than half of Earth. On balance, they cool it. Low clouds cool Earth more than they warm it, but high ones do the reverse. So, changes in cloud area, altitude, and opaqueness affect global temperature. The area is shrinking a little for warming trend. More high clouds, fewer low ones for warming trend, and more opaque for cooling trend. The net result, as we see on the next slide, is a warming trend. This analysis is about 2.5 years old. The low amount is the biggest warming factor, followed by high altitude, and there's a small one for less opaque. The clouds are getting more opaque, but that's not as big a factor. The estimate from the IPCC is a bit higher than the estimate that I'm using in my climate futures, which you'll see later. But the cloud changes add a lot to warming that would otherwise happen. Now we'll move on to the next subject, sulfates. Dark sulfates in the air block sunlight that cools Earth. They make haze, become cloud condensation nuclei. More sulfates, cloudier, cooler, acid rain. More sulfates come from burning coal, some from volcanoes. Also dimethyl sulfide coming from plankton in the ocean. Greenhouse gases stay in the air many years, sulfates usually for days. Sulfates do not keep rising. Actually, they've come down by 1/4 from their peak in 1979. That's why I say formerly 40%. Now they offset 30% of warming. But you get rid of the sulfates, you get a big pulse of warming. Well, medium-sized pulse. So what's happened with sulfates really explains why the temperature record does not rise as smoothly as the greenhouse gas record. So let's go through a few of the more major episodes and see what's going on. Volcanoes are a big factor. They put a lot of sulfur in the stratosphere for a year, even 2 years. Things cool off for a while. Humans started doing really major things by putting sulfates from coal in the air from 1940 to 1970. There's another volcano. And then we started taking sulfur out of our smokestacks. So the sulfate levels went down starting in 1975. As I mentioned, they're down 23% from their peak. They've been fairly stable for the last 10 or 15 years. What you see is we've already seen 1.8 degrees Celsius warming from the trough a little bit after 1880, Krakatoa, to currently. That's pretty close to 2 degrees Celsius already warming on land. The next topic, Arctic sea ice. The area has been going down semi-steadily. It's down to almost down to half of what it once was. The sea ice volume is down to more like a quarter of what it was. What's happening, the ice got thinner too. And as the diagram much earlier at the beginning showed, as ice recedes or Earth absorbs more heat and it will get warmer. Here's a picture 36 years apart, and you can see considerably less ice north of Alaska and eastern Siberia and central Siberia and pretty much all along the Siberian coast. That Arctic sea ice, well, here's the picture of Arctic sea ice volume in the major months. September is the minimum month, July and November are about the same, June and January about the same. And what you see is Arctic sea ice will be gone for a short period of time, somewhere in the 2020s, be gone for maybe 3 or 4 months at a time. In the 2030s, will be gone at least half the year. In the 2050s, going to be completely gone before the end of the century. That's what those trends tell us. Trends could change. So looking at both the Arctic and the Antarctic sea ice, Hudson estimated the total Arctic sea ice loss would warm Earth's surface by 0.7 watts per square meter. 0.1 had already occurred, a little bit more than that now. Antarctic sea ice is a similar area, but it's not clear that the loss has begun, although we've hit record lows in the last 3 years, so maybe it's begun. Okay, next topic, snow. A couple perspectives on this. This is one study, came out about 4 years ago from Chen. That's the change in radiative forcing, so the Earth gets warmer, and that added about 12% greenhouse gas warming. That's my translation. Then I did some analysis of my own that's not just about timing, but about how much snow is there and all through the year. And you notice that there's a lot less snow in New Orleans than Winnipeg. Snow stays a lot longer where it's colder. So I did an analysis across 14 cities to look at that. And I found that when a lot of adjustments were made, that snow decreases 8.5% per degree global surface warming. So about 12 degrees, snow is absent from Earth. Maybe a little bit low estimate. And then land ice. That's where we worry about sea level rise. Greenland's ice melt rate is going way up. Antarctica is losing only half as much ice, but has a lot more. But its ice rate is also going up something like 12% a year. Land ice area decreases far more slowly than sea ice area because the ice is thick. So its albedo change effect is much slower, and there's been very little of it so far because it's so much slower than the Arctic sea ice loss in terms of area affected. So I'd like to take another pause here. We're going to use these information to project. We're going to look at putting this together for the past 45 years. You doing a 3, 2, 1?
Yes.
Oh, okay. So just a quick review. The feedbacks that we've talked about were water vapor, clouds, sulfates, sea ice, snow, and land ice. We're going to put those together, which I did. Have to look at my paper for details. 39% of the warming over those 41 years came from albedo or reflectivity changes, direct and indirect. You can go back and look at this later, and that table, of course, is in my paper, table 2 in the paper. So the 39% comes from 0.33 degrees Celsius, which is over at the right bottom of the table, to the amount total surface warming over those 41 years, which is 0.839 degrees Celsius. Warming to 2100, and especially beyond that, will be dominated by albedo changes and their feedbacks. It's likely that we humans will not be emitting carbon after 2050, and it's almost certain that we will not be doing so after 2100. So these albedo changes will become more dominant in the future than they are now. Some of them will become stronger and operating faster than they do now, and some will not. So let's take a look. Now I'm going to split the cloud and water vapor feedback out separately, and I'm going to do that not only for the albedo effects, but also for our greenhouse gas emissions. A lot of the warming due to our greenhouse gases is actually due to the warming from the water vapor from when our greenhouse gases make the surface warmer. So we're going to split that out, distributing them, is what I call, and apply to those 41 years. More water vapor is the biggest factor, followed by more CO2. Then fewer sulfates, then the cloud changes, and the methane. Then we have earlier snow melt and other greenhouse gases. And then we have less Arctic sea ice. Of course, we'll have 7 times as much Arctic sea ice, plus it's also that same amount of Antarctic sea ice. So our emissions, 32%, albedo changes, 32%, water vapor, 36%. That's our somewhat recent past. Then another thing which is not an albedo effect, it is a feedback and a kind of a tipping point. Permafrost emissions up through 2000 were probably close to negligible. They are appreciable now, but not large. They're going to get much larger than they are now. It depends on the local temperatures. Here are some estimates by the first study that I'm aware of, and there have been precious few studies that have looked at future permafrost emissions. And these are looking anywhere from 0.2 to 1.6 degree Celsius warming, depending on the temperatures. I would say about the DEP, these are emission scenarios, but the amount of warming you get from the various emissions is a good bit higher than you will see in the scientific literature, because they've underestimated the albedo effects, which also cause warming. So the impacts of those factors will continue. They will be much greater in the future, at least for a few centuries, until Earth's ice and snow are gone. So the numbers, my best estimate. Earth will warm almost 4 times more even if we stop emitting now. Sulfur emissions from coal, about 0.4 Celsius. Vanishing polar sea ice, about the same for each of the 2 poles. Snow, about the same. Permafrost, about the same. A bit less from land ice. And warming the oceans enough so energy out balances energy in. And then finally, the multiplier for water vapor and cloud cover, which apply both to greenhouse gases and to albedo effects. They're applied here to the albedo effects. Suppose we don't stop cold turkey, but keep on emitting. I think 2035 is probably about the longest it's going to be till they peak. you get a lot more warming. Those are the factors. Other factors include clouds, land ice, and various other things. That's a good bit more heating than stopping emissions now. Moreover, warming in that case continues long after 2400. You'll see this in the climate futures. So, using these factors about greenhouse gas emissions, both those that we've done already and those in our future, these are choice variables we have, and the albedo feedbacks and the permafrost feedbacks, and other things like permafrost, like methane hydrates, soils that will emit carbon more as they grow warmer, and oceans, which will also emit more carbon as they grow warmer and gases become less soluble. So here are the emissions pathways which we can choose. I did 6 scenarios. XFS means no fossil fuels or phase out fossil fuels, such as by 2050. CDR is carbon dioxide removal. So soil carbon loss since 10,000 BC is 60% of fossil fuel emissions to that date, which is more like 40% of our fossil fuel emissions so far. Some of that soil is gone, but about half of it is just carbon depleted. So we can put some carbon in soil. Here's what it translates to in parts per million. That's much more than just our own emissions. Those are the feedbacks from permafrost, methane hydrates, soil carbon, and degassing from the warmer ocean surface. I'll look now just at the next century in the detail, and then we'll go and look out to 2400. You notice that if we stop cold turkey, stop emitting carbon right now, the temperature goes up more than if we didn't. That's the sulfate haze that was screening warming out is no longer doing so. But in the out years, you're on a lower trajectory by doing that. So the range is from a little less than 3 if we're very good at carbon dioxide removal to about 4.5 if we do the stupid thing and take another 15 years to achieve a peak in our emissions. There's good reason to think the peak in emissions from electricity may already have happened, and the peak from oil use will happen before 2030, but I'll let Rick Riss get into that later. So here's the temperature out to 2400, the same 6 scenarios. And now we're seeing that taking CO2 out of the atmosphere, the more of it we do, the closer and sooner we come to 2 degrees Celsius on the way back down. If we stop now, we can maybe avoid 5 degrees, which is when Kansas gets hot as Las Vegas is now. This includes the big albedo effects, loss of sulfates and sea ice, loss of some snow, cloud cover, and land ice. In the black case, loss of almost all snow. Land ice loss is going to go on for many centuries. So when we get as hot as Las Vegas now, that's when civilization starts to fall apart. When you can say civilization has fallen apart. 10 degrees, which is the black line, about 2500, threatens extinction. So let me pause there. Hi, welcome back. Just a note about what I said shortly before I paused. 2035, I think, is later than we will actually peak. The peak in emissions from electricity may very well have already happened. Solar and wind are cheaper than any other kind of electricity source now in most of the US and in most of the world, and that will get even more so in the future. The other major emission is transportation and petroleum. The emissions are likely to peak this decade and go down somewhat steeply, and that's due to the falling price of batteries to power vehicles. Right now, UPS, Walmart, Amazon, etc., all the new vehicles they're ordering are electric for their delivery vans, and they're starting to order electric semis, 18-wheelers. What happens is when you do that, you get progressively less petroleum used for transportation. The personal vehicles follow that. You also have the self-driving revolution, which reinforces that. So let me go on to our task here. These solutions, obviously, stop putting carbon in the air as soon as reasonably possible. Take carbon out of the air. If we can't do that, we're gone. 3/4 of what we added so far, any future emissions, the sooner the better. Probably going to need to screen out sunshine too, but that's for another day. So quick table of contents: personal, 4 on policy, 1 on carbon-free technologies, and 2 on CO2 removal. So what Jane and I have done, we have a heat pump, air source, electric car, 100% green electricity as we have for many years, community solar on top of that, and CO2 removal. We've just done a little bit so far. Pay other people to do that. As a result, we've cut our carbon footprint by 80%. But individual stuff like us isn't going to cut it because not everybody is committed as we are. Policy: tax carbon across fossil fuels worldwide in proportion to carbon content, impose a tax upstream, start low, rise briskly on a preset path, return the proceeds as dividends to individuals, also end subsidies. That's a statement by the world's leading economists, and the US leading economists agreed with that about 3 years later. So what would one look like? Citizen Climate Lobby, which I've been involved with for some years now, proposes $15 per ton of CO2 to start, rising $10 per ton per year. The proposal we've had for all these years is now in Congress with 80 co-sponsors. It includes a border tariff adjustment for difference between our carbon price and other nations. Economic analysis of the proposal shows that this path creates jobs and grows the economy compared to life without it. 70% of Americans receive more in dividends than they pay out due to higher energy prices. It's an especially good deal for low-income Americans who mostly use a lot less energy. Emissions fall 50% in 20 years. That's a good start, and even saves a few lives. The other thing we need to do is pay for verified CO2 removal at the same price as CO2 emissions. That's my point. I'm not sure I found anyone who disagrees with it. Rick will talk later about technologies to reduce our emissions. Jim and Meg will talk later about En-ROADS, a model where you can choose policies and technologies to affect emissions and temperature. Make sure you choose a high climate sensitivity to get realistic picture. Okay, taking carbon out of the air. First, the biological methods. Farming, 4.3 gigatons of CO2 per year into soils. That's about 11% of our emissions now, $20 to $100 a ton. Organic farms are the gold standard, particularly no-till and compost cover. If we can rebuild soil organic matter from what it is now to what it was before farming started, that can take care of about 20% of what we need to do. Farm the oceans. There's huge debate on how effective this is. But anyway, you're probably going to need to add fertilizer, and question, you do it near shore where there's a lot of nutrients or farther out where there's very few nutrients. Biochar is very good as far as it goes, maybe 1 or 2%, maybe even 3% of what needs to be done. Rangelands, that's a big question mark. Short rotation cattle grazing, also known as holistic management. If you feed cows red seaweed, something aspergensis, it cuts down their methane bursts by up to 98%. Trees are wonderful. Unfortunately, our future is going to have less of them because forest fires are going to run wild in a warmer world. The non-biological methods, direct air capture. A lot of people are working on this. Blow air through catalyst in artificial leaves or ceramics. Klaus Lochner pioneered this. Climeworks is who we get it for $1,000 a ton, but Dave Keith out of Harvard and Carbon Engineering is looking at 138 once it scales up. It's very easy to turn it to rock, and it's going to stay locked away for tens of millions of years. Rock weathering, speed it up by presenting a lot more surface area for the chemical reactions. Same thing by spreading it on the ocean surface itself, makes it more alkaline, less acid. And you can also tread on farming soils. Dan Kittredge will talk about that next week. And that's an excellent fertilizer, probably better than any artificial fertilizer. So, in summary, we must go carbon negative big time by 2050. Time for more questions. There's my contact information. My draft paper with all the details is on my website at the bottom of the second page of the